Hello and welcome back to differential equations. Today we are talking about 3.2 section, which is the section on series solutions near ordinary points. What is it? So let's just take a look first. What is this? What this means? Series solutions near ordinary. So power series can be used to solve a wide variety of differential equations, linear and nonlinear, of any order. But we are primarily using them to solve the second order differential equations that have the form like this, where these ax, bx, and cx are some functions of x. So this is, as you can see, second order homogeneous equation, but these are no longer constant coefficients. They are now ax, bx, cx. These are whatever functions. And we can assume a solution of some sort and then plug stuff in and work it out. So we can change this around by dividing through by ax, right? That was one of the older tricks. So if we divide by ax, we will arrive at y double prime plus bx over ax y prime plus cx over ax y equals 0, and then just rename these functions into p of x y prime plus q of x y equals to 0. So these are the things. So now when you look at all of these, right? When you look at all of these things, we can solve these equations using using series solution. Let's take a look at some of these. And I want to, first example that I want to introduce, I actually want to use constant coefficients because that's the easy one. And then we'll see what else we can work with. So let's go with the first example. Say y double prime plus y is equal to 0. Now, solving this equation, we know how to do this, right? But let's do it using series. So you know that you are expecting the complex roots here, which means that the solution will be the good old sine plus cosine, right? So we're hoping to find that in our solution using series, the same one. So I will start with assuming the solution of the form Cn x to the n, right, where n starts at 0, goes to infinity. And then we said that when we differentiate this, because we have to plug everything in, the counter shifts by 1, and we have n times Cn x to the n minus 1. But then we said when we shift counter back, right, we get n equals 0 to infinity, and then we have, was it n minus 1? Oh, well, let me just check if the stream is going. Yes, stream is going, good. What was the, let me see, the last class we did shifting the counters, so it was n plus 1. Yes, n plus 1 Cn plus 1. So n plus 1 Cn plus 1, and then x to the n. And then when we take the second derivative, looking at the first, the counter shifts one more time. We get n minus 1 times n times Cn times x to the n minus 2. And we get, when we shift the counter back, we get n plus 1 and then n plus 2 and Cn plus 2 and then x to the n. So now we plug these into differential equation. We have the series n starts at 0, goes to infinity, n plus 1, n plus 2, Cn plus 2, x to the n, plus summation of, well, n goes 0 to infinity, of Cn x to the n equals to 0. Since we have x to the n on both, we have the summation on both, that starts at 0. We can combine all of this into one expression. Maybe I can put these brackets now. So n plus 1, n plus 2, Cn plus 2, plus Cn, and times x to the n equals to 0. So we said that last time, in order for this to be equal to 0, we don't want the trivial solution. So xn is not 0, which means that this equation here must be equal to 0 in order to solve this. So we are getting n plus 1, n plus 2, Cn plus 2, plus Cn equals to 0. So now that we have this, we go and write those cases. So we start at n equals to 0. So for n equals to 0, I have 1 times 2 times C2 plus C0 equals to 0. And from there I can solve for C2. C2 is equal to negative C0 divided by 1 times 2. And I'm not going to say it is 2 because I might need to see a factorial pattern. So leave it as 1 times 2. Let's compute this equation for n equals to 1. That's going to be 2 times 3 times C3 plus C1, from where C3 is equal to negative C1 divided by 2 times 3. Great. Now we compute the next one. N equals to 2. N equals to 2 is going to be 3 times 4 times C4 plus C2 is equal to 0, from where C4 is equal to what? C4 is equal to negative C2 divided by 3 times 4. But hold on, I know what C2 is, right? C2 is this expression, which means that this whole thing becomes positive C0 divided by 1 times 2 times 3 times 4. When you plug in, work out the algebra, you get this. Then we go n equals to 3. That's 4 times 5, C5 plus C3 equals to 0, from where C5 is equal to negative C3 divided by 4 times 5. But we know what C3 is. it's negative C1, so that kills a negative. So it's just going to be C1 divided by 2 times 3 times 4 times 5. I'll do 2 more. N equals to 4 and n equals to 5. So n equals to 4 is 5 times 6, C6 plus C4, from where C6 is equal to negative C4 divided by 5 times 6. But we know what C4 is. It's C0. So negative C0 divided by 1 times 2 times 3 times 4 times 5 times 6. And the last one I'm going to do, because the pattern is already obvious, is 5, which is 6 times 7 times C7 plus C5 equals to 0, from where C7 is equal to negative C5 divided by 6 times 7, but C5 is already given as a C1, so that's a negative C1 divided by 2 times 3 times 4 times 5 times 6 times 7. Now, what you are seeing here is a solution. Now, it looks crazy, but if you carefully look into this, right, these are all coefficients of x to the n, right? And x to the n carries the exponents that would mimic this behavior of even and odd. So I hope you see from this pattern sines and cosines. I hope you see a distinct pattern that deals only with even, and all of them are dependent on C0, and a pattern of odds that are all. So it's like two different groups, like two strains. You have a C2, which is connected to C0, and then C4, C2, C0, C6, C4, C0, through C2 again. And then you have the other strain, which is C3, C1, C3, C1, C5, C7, C5, C3 that plays into C1. So two separate worlds, right, of these. Now what's happening with exponents that are attached to this? So if you, now that we have these guys, I am going to write this as, well, C0 is its own master times x to the n is 0. Then I have another term, which is C1 with x to the 1. And then I have C2, but C2 is in charge, it's a negative C0 over 2 factorial. So C2 is C0 over 2 factorial, and then it's x squared, right, because n is 2. Remember, you are starting from series Cn x to the n. So whatever exponent you are using, it's x to that value. So then I have, now this one was negative, right? C2 was negative, so that's a negative right there. Then the next one with the 3, is negative C1 over 3 factorial x cubed. The next term is C4, which is C0 over 4 factorial x to the 4. The next term is the one with the C5, which is C1 divided by 5 factorial x to the 5. And I have two more. There is a C6, which is again negative C0 over 6 factorial x to the 6. And the last one, C7, which is negative C1 over 7 factorial x to the 7. So we clearly have terms that are dependent. I'm not sure why am I putting these commas here. What the hell? This is not sequence, this is a series. These are all pluses. Here, I'll put them in blood. They're all pluses there. And now I hope that you can sort through this and pick off all of the terms that have C zeros and pick off all of the terms that have C ones. So if I am to, so this is a solution, y equals, right? So y equals, let me factor out C0, see what I get. So C0, x to the 0 is 1, so I have 1. And then I have minus 1 over 2 factorial x squared. And then I have plus 1 over 4 factorial x to the 4th. And then I have minus, for C0, 1 over 6 factorial x to the 6th. Do you all see that? And then I'm going to add plus C1 and put all of its factors there, which is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5, and then minus 1 over 7 factorial x to the 7. Now these will go forever. So what are these? If you pay attention, right, last class when I talked about sines and cosines, you will quickly recognize them as the C0 cosine x plus C1 sine x, which is the solution to the original equation. Now, obviously, there's a much easier way to solve than this. I mean, this is not hard. It's just really messy and long. But same principle applies to every problem. So this is the simplest example that you can possibly encounter in this chapter, because we are dealing with the constant coefficient, right? Very basic sine and cosine equation. All right, so I'm going to one more time go through the whole process, and then we're going to take a look at other examples. So we assume the solution y equals. Now, guys, this is a solution for which I want to find values. So y is the solution. That's what we're looking for. And I differentiate that twice. And when I differentiate it twice, I have to shift the counter, right, to go back into the original problem. And then after that, I can plug everything in. So now when I have this, pen, come on, pen. No, it's exam tomorrow. I already have it in my office. I got it not even 15 minutes before I walked in here, so I didn't have a chance to set it up. Maybe we could cancel the class and I set it up now. All right, so I have that. Then I take the two derivatives and shift the counter. Plug this one there, this one there, right? You will be plugging where they belong. Once you plug them in, you come up with this expression. And then since they have the same summation starting at 0, and they have the same x to the n, which can be factored, we come up with this expression here. Now, in order for something to equal to 0, two factors, right? It's either first factor is equal to 0 or the second factor is equal to 0. Now, second factor is x to the n, and you don't want that to be 0 because that leads to a trivial solution, ignoring all others. So we don't set that one equal to 0. We set this relationship here equal to 0, which is what gives us this equation. Once you have this recurrence equation, all you need to do is to crank and simplify for n equals 0, 1, 2, 3. So this busy work is just figuring out what's happening here. So for n equals 0, take the equation, plug 0 for every n, compute, and then simplify. And you always want to simplify in terms of the higher exponent because you can express that one hopefully in terms of the lower one in the sequence. So we find, this would be a good enough amount, about 6 or 7 of these. You don't have to go overboard, compute 30, but you definitely can't see anything if you compute, 3 or 4. You can't see the pattern if it's, broken between a few of these terms. Then we put the series together for each one of those. And then when I factor out all the terms with C0 and I factor out all the terms with C1, we come up with the answer. Now, we know that this is correct and this is good answer because we know how to solve this equation using constant coefficients, which I can do here as a check on the side. All I need to do is to say that's r squared plus 1 equals to 0, from where r is equal to plus minus I. Right? And that yields this answer right away using chapter 2. I remember last time before we ended the class, I quickly outlined the problem that actually had the minus sign. I did that on a board, minus sign, and we got our hyperbolic sine and cosine solution for this. Now that I think about it, I kind of think he has some kind of organs or something inside. That's just too much love for the cooler. Passed out. I don't know. Let's take a look at one of the equations from the homework because we can. Any of these works. Number 8 is fine. So we have 2 minus x squared y double prime minus xy prime plus 16y equals to 0. As you can see, we have, this is your ax, right? And then b of x is just x. And then c of x is just 16. So you do have these functions, and we use series solution to solve this. So we assume solution y equals summation n goes from 0 to infinity of cn x to the n. From where we take the first derivative, the counter shifts by 1, so we have n cn x to the n minus 1, but then when you shift the counter, so it's n equals to 0 for the start, and rename everything, you get n plus 1, cn plus 1, and then x to the n. Now some of you would ask, can I just memorize this? And the answer to that is yes, you can. But if you want to think and annoy others, you obviously should know how to get it. So we have this, and then n minus 1, cn x to the n minus 2, which gives us the summation of, when we shift the counter, we did this last time, n plus 2, n plus 1, and then Cn plus 2 and x to the n. So now it's our job to plug this into differential equation. Note that you will be multiplying by 2 minus x squared. So pre-multiply 2 minus x squared times the summation of n plus 2, n plus 1, Cn plus 2, x to the n from 0 to infinity, minus x times the summation of n plus 1, Cn plus 1, x to the n. And ooh, we did not have to shift the counter for this one. Let's see what we get. Plus 16 times summation Cn x to the n equals to 0. Yeah, everything is, the stuff is not matching now. Our ends are aligned, but x's are not. See that? Because when this goes inside, this becomes n plus 2. And this becomes n plus 1. And this stays xn. So they're no longer aligned. So we don't shift the counter here. We don't plug in these. We plug in the raw form. So you either plug in one or the other. So let me go back and plug in the raw form, and then we'll see if we get better solution. I hope you see why this can't be solved this way. Right? As I distribute this inside, this becomes x to the n plus 2, because x squared, right, times x to the n is x to the n plus 2. And then all of the x's will be off by exponent. So what I'm going to do instead, I'm just going to erase everything, don't worry about it. I'm going to plug in the original. So second derivative first. And then, what do we have? Minus x times summation n starts at 1, goes to infinity. I'll show you what you do. You peel off the extra terms. So if the counter did not match. Okay, all of that. And then x times n plus 1 Cn, no, n Cn, x to the n minus 1, and finally plus 16. Is it plus 16? Yep, plus 16. Y, which is summation of Cn x n, equals 0. Now, these guys go inside. So as I multiply, over here I am going to get two series. There is going to be a series which is multiplied by 2. So the series of 2n, n minus 1, Cn x to the n minus 2, where the counter starts at 2. And then we have minus because there is a minus sign there, and you have x squared, which can go inside the summation because the summation operates on n's, not on x's. So x is like a variable. And we have x n n minus 1, c n x. It's x squared. There we go. N minus 2. Good. Now we have minus. X goes inside. So summation of x times n cn xn minus 1 from 1 to infinity. And then finally plus 16 summation cn x to the n equals 0. Holy nightmare. Awesome problem. I love it. So now look what happens. This guy will have to shift stuff around so that we can actually match the exponents and things. So we'll deal with that term eventually. So summation 2n n minus 1 cn xn minus 2 from 2 to infinity. And now here, this guy and this guy multiply. So I get minus summation n minus 1, and then this is just x to the n. Minus, again, the sx multiplies in there. So we have summation 1 to infinity of n cn x to the n. And the last term is just plus 16 summation from 0 to infinity cn x to the n. So we are happy. We are happy when we see all of these exponents line up. It's important for exponents to line up because we have to factor exponent. So x to the n. So it's important to have x to the n everywhere. Well, I don't have x to the n here, right? But not a big deal. I can do the transformation here, and it will shift. It will change some of the stuff inside, but I have to have that x to the n there. So the first term now requires a massage in terms of flipping it around a little bit. So what I need to achieve is this to be just n. So for now I'm going to call it k. Right? But remember that for the sum over here, you have n equals to 2. Well, you are stuck with n is equal to k plus 2, so you can't do anything about that. So what you get here is, so I'm just transforming this term. Summation, n is k plus 2 is equal to 2, infinity, and then 2, n is k plus 2 times k plus 2 minus 1 times c of k plus 2 times x to the k. So I'm just transforming this one term. So now when I subtract 2 on both sides, I get k is equal to 0, infinity. I can kick this 2 outside if I want to, in front of the sum. And I have k plus 2 times k plus 1 times ck plus 2 times x to the k. And now we do the trick of just renaming k's back into n's. So n is equal to 0 as infinity on top. And then we have k plus 2, k plus 1. So n plus 2, n plus 1. C, n plus 2. And then we have x to the n. And that's that first piece. So all of this is this. Because now, and look, we achieved what we needed, x to the n. So now every single one has x to the n. That's what we need. That's why we had to, shift it a little bit. So now what do I have? I have my differential equation as the solution, to summation n from 0 to infinity of n plus 2, n plus 1, c n plus 2 x to the n. And now copy the other three terms. Minus summation from 2 to infinity of, where is the simple form? There is. That's the second term, right? So summation of n minus 1 x to the n. And then next one is minus summation of n c n x. And that counter goes from somewhere to somewhere, from 1 to infinity. And finally, the last term is 16 times summation of Cn x to the n. That's the vanilla state. 0 to infinity. Equal to 0. So I hope you guys see what I did. I had to transform only one of these. So now we have to get all of these guys to match. And as you can see, in some are 0, some are 2, some are 1, which is a problem. Now, how do we get them everywhere? Well, think about it. I already matched all x to the n. They're all x to the n. And if I mess with this in any other way, I'm going to mess that up, right? I worked hard and I lined up all x to the n's. But I need counters to be the same. But they're not. Now, what we are going to do is we are going to agree on a counter where all can start coexisting and peel off the terms that are extras, right? So if you take a look here, this term is n equals to 2. That's a third term, right? You have n equals 0, n equals 1, n equals 2, right? So n equals 2 is the third term. So every single one of these will have to start there, right? Which means that I have to peel off first two terms of this and set them aside, one term from here, set it aside, and two terms from here and set it aside, and then all of the series will start at 2, and then I will be able to actually do the pattern that we did for this. And the 5 things that I peeled off, they will be just in front of our solution. And the rest will follow from there. And when I start doing the pattern, I start with n equals 2, and then n equals 3, and 4, and 5, if I can find the pattern that will fit back into the equation. So I'm going to start my pattern. Oh, sorry, before I start the pattern, I have to peel off all of the terms that I can't keep. Well, n equals 0, I'm peeling that. So for n equals to 0, I will have 2 times 2 times 1, C2 times x to the 0 is 1. And I also have to peel off from that one, I also have to peel off n equals 1. So 2 times 3 times 2 times 3 times 2 times C3 times X. Cool. Now the rest of that series stays. You know, I'm going to put this 2 inside actually, because we'll need that. And now counter starts at 2. Let me make that 2 red. So the reason why we pull the first 2 terms is that the counter starts at 2. Now I'm moving on to the second series, and the second series starts at 2, so don't touch it. Minus the series n minus 1 x to the n. It starts at 2, so I'm happy there. Nothing to do. Keep moving on. Now we're going on to the third series here. It starts at 1, n equals 1. But I needed to start at 2, which means peel 1 off. It's a minus there. So we'll be subtracting that n equals to 1 term. And that's 1 times C1 times x to the 1. And then we have minus the rest of the series, but now that series starts from 2. And finally, we arrive at the fourth series, which unfortunately starts at 0. I have to peel off 2 terms. I peel off 0 term first. The last series is added, so plus. I will have 16C0, x to the 0 is 1, plus 16C1 times x, and then plus the rest of the series will start at 2. So now I can finally copy everything. Yes?
You're missing the Cn for the second explanation.
Oh yes, I'm missing over here, right? There's no C term inside. Has to be a C. Now I just need to put it in. It's not a mistake. It's just oversight. So which one was it? Now that's this term that it's missing it, which is the second term. Oh damn! I didn't put it anywhere. So this term is missing it. So that comes from here. So it's just a basic Cn, right? That's what's missing. So I have to put in a Cn in here, which needs a Cn in here, which now brings us to have a Cn in here. There we go, fixed. Thank you. Holy nightmare. That would definitely ruin everything. Now compute all of the other terms that you can. 2 times 2, so that's 2C2 plus 12C3x and I'm going to first deal with all of the non-series terms. So minus C1x plus 16C0 plus 16C1 x plus, and now we put 4 series together which all start at the same counter, all have x to the n, so we can all factor everything there. So plus the series, it starts at 2, goes to infinity, and in bracket here I have 2, n plus 2, n plus 1, Cn plus 2 minus n minus 1 Cn minus n Cn and plus Cn, all of that time x to the n, equal to 0. Beautiful, huh? So now we can simplify and combine some stuff, hopefully. Start with the C0 term first. So that would be 16C0. Now C1s. You have a 16 C1s over here and 1 over there. So that's 15 C1 times x. And then plus 2C2 plus 12C3x plus the summation of the whole thing times x to the n equals to 0. Yay. All right, so now the insides over here can also simplify. As I'm writing my equation, so let me just make sure that you know that all of this goes there. And now that recursion equation is 2 times n plus 2 n plus 1 times Cn plus 2. Isn't some of these supposed to be n plus 1? Cn plus 1? At least one of these. Oh no, because we kept the original one. Okay, good. Yeah, they didn't shift. Okay, so Cn plus 2. And now I can combine all of these Cn's, right? I can just say plus, and in this whole parenthesis, and just have Cn over here, and all of that equal to 0. Now, what do I have for Cn? I have minus n squared plus n minus n plus 1, and these guys drop, so it's 1 minus n squared. Nice. So I have 2 n plus 2 n plus 1 Cn plus 2 plus 1 minus n squared Cn equals to 0. And now we start our pattern. But we start from n equals to 2. Observe. me. Yeah, that's it. We're done. We're done for this semester. Teach differential equations next semester when my voice gets better. So for n equals to 2, I have 2 times 4 times 3, no coughing, C4, plus 1 minus 4 times C2 equals to 0. So 24C4 minus 3C2 is equal to 0. I need to solve for C4. So C4 is C2 over 8, right? Does that make sense, or just no one cares? Huh? That's right. Yay. N equals to 3. So for n equals to 3, like this is our boss equation that we are looking at, right? N equals to 3. I have 2 times 5 times 4 C5 plus 1 minus 9 C3 equals to 0. So from there I can calculate C5. Actually, let me go one more step for calculations. That's 40 C5 minus 8 C3. And from there, C5 is equal to something. Is that C3 over 5? Let's call it C3 over 5. Good enough, right? I'll compute one more. I'm already getting tired. 2 times 6 times 5 plus 1 minus 16 C4 equals to 0. So that's a 3060 C. Oh, I forgot the C6 over here, right? C6 plus, no, minus 15 C4 equals 0. Now I'll compute one more. C6 is equal to quarter. So that's going to be C4 over a quarter, so over 4. But we know that the C4 is C2 over 8. So this is C2 over 32, actually. And just one more. And 5 is 2 times 7 times 6 C7 minus, no, plus 1 minus 25 C5, which equals to 0. 6 times 7? No one knows? Okay. Yep, I know, that's the hard part, right? Plus, no, minus 24 C5, which equals to 0. From where C7 is equal to 84, that's wait. 7 times 6 is 42 times 2. 42 times 2 is 84, right? And 1 minus 25 is 24, but 84 is not divisible by 24. We can cancel 24 over 84 by 4, get 6 over 21, cancel it by 3, I get 2 7ths. Huh? Are you happy with that? Whatever, huh? So 2C5 over 7. But then we know that the C5 is over 5, C3 over 5, so 2C3 over 35. So what's the solution? I don't see any pattern here. What's the solution? Y solution is all of the terms that we pooled, 16C0 plus 15C1x plus 2C2 and you see that those are 12C3x. So those are the first terms. Now we have all of the other terms that we computed through a series. You have your C4. You see how the last one was C3 that came out as a free from when we peeled off terms? And now the next term would be C4, but that's the first one we computed when we did n equals 2. I mean, this stuff is just amazing. So now this one is C2 over 8. That's a C4, which is in terms of C2. So C2 over 8, and then x squared, right? It's x squared because remember that the sequence was Cn x to the n. And when we do n equals to 2, right, that was the next one. So the next one is C5, which was C3 over 5 x cubed, plus the next one is C4, which is C2 over 32 times x to the 4th power. And then this is the x to the 5, plus it goes forever. This was 2C3 over 35. Now we rearrange the answer in terms of the constants which keep appearing. So you have your C0, you have a C1, but then you have a whole bunch of these in terms of C2 and C3. So we factor out C2, factor out C3, and write all of the other terms in terms of those. And then those might produce a pattern that we can write the function for. I don't see it for this one, but let's just write it out, see what happens. So 16C0 plus 15C1x plus 2C2. Is this the C2 we need? Yes. So I'm factoring C2. And what do I get? I get 2 plus 1 over 8x squared plus 1 over 32x to the 4 plus, ooh, there might be something there, right? Plus 3 dots because these will go on forever. Plus, I am pulling C3 now, and let's see what we get for C3. We get 12x plus 1/5 x cubed plus 2 over 35 x to the 5th plus, and that will go on forever. Now I'm wondering if this would give me anything, because these exponents are they're looking cool. If I am to pull out 1 over 8, let's say, I would have 16 and then 1 and then a half. Now maybe we could put something. Ooh, well, what are you going to do for downstairs? You have 5 and 35, so it's going to be a 7, but the 12 is off, unless I made a mistake calculation somewhere. Yeah, but that's a solution. This is it. Your solution is now in terms of polynomial. You figure out which precision you want. You keep, remember, power series, right? Keep 3 terms. You have 4 constants here. C0, C1, C2, C3. So you better have 4 conditions to find them, right? If you are to find these things. But there it is. So this is a solution. It looks messy, but at the end, guys, please realize this solution is just a polynomial. When you throw away terms after, where those 3 dots are, just throw everything away, and you will be able to actually put this into a polynomial that has x squared, x, and a constant term. Once you do that, differentiate once, differentiate twice, plug it back in the original equations, figure out, right, with our initial conditions to find C0, C1, C2, and C3. Do you see now why it's called power series? Like, you can solve anything now, anything. And it doesn't have to, collapse onto sine and cosine hyperbolic or just basic sine and cosine. It doesn't have to be constant coefficient. You can literally have any function there, and if the coefficients and exponents don't match up, don't worry about it. Match up exponents, and then peel off the extra terms, and then just grind through the rest. That's how awesome this stuff is. This class ends at 4:50, right? So we have time to finish off more. So these recurrence relations, so what I used to, what you call the boss equation, okay? That's called the recurrence equation. And we use it to figure out the pattern of coefficients, and then we can just attach all of the x to the power that we need and so on. So recurrence equation, and in the previous example we also had the recurrence equation, just like 10 years ago, so there it is. Recurrence equation, so you know what it is, the name. What we just solved is a particular example of something that is called Legendre equation. Legendre equation has the form of 1 minus x squared plus the y double prime plus xy prime, and then it has that this 16 is given in terms of parameters alpha, so alpha times alpha minus 1. Sorry, alpha plus 1. And that one can be, you can figure out how to fit 16 into that right format. So all of this can be done. There is a generalized solution for Legendre equations, but memorizing that would be just insane, so don't. All right. It's the procedure. And you see how interesting the next exam is going to be, right? with each problem taking like 3 hours to do. So hopefully, the following weekend will be heavily influenced by differential equations in terms of these calculations. Yeah, we did the second example. Second example took a little bit more time, and that was problem number 8. So, right, that was the fun. They go up to 15, and then they start getting worse after that. What are the shifted series? Shifted series are Taylor approximations of the x minus a in parentheses when you do expansion around the point away from 0. In this case, I assume the solution Cn x to the n because my expansion happened around 0 because I was interested to see what is the solution to differential equation in that region. But say that your initial condition is away from there, and you remember in the power series are approximations. If your differential equation is centered at 7 and you expand around 0, solution that you get might be a complete garbage because it's just far away. Even 1 is far away. So we are supposed to expand around the point that we're interested in. So you look at your initial conditions. Now, how does that change the whole thing? It really doesn't change much, except you will be dragging x minus a throughout your calculation. So from practical point, there's really not much to to worry about. You'll just be dragging x minus a. I don't think they call it centered. They call it translated series solutions in the textbook. And the solution is Cn x minus a to the n, as I said. So why is that so? Because initial condition was provided to you, and it was said, here it is. So y of 1 is 4, and y prime of 1 is negative 1. So you should be expanding around x minus 1, right? Or t minus 1, depending on what your input variable is. So you'll just be dragging that throughout. The calculation stays identical. It's just that you have to be aware that your Taylor series must be centered in the area of interest. You can't just go and put the Taylor series anywhere and just walk away, right? You have to do it specific. So let's take about 16 seconds to kind of reboot. I'm not going to stop the stream. It's just going to be silent for some time to reboot, and then we'll do one more example of this. So you have one more example to look at, and then call it a day, because registrar said you guys are busy.
Classes start tomorrow, right?
Complex is tomorrow, yes. So complex variables tomorrow at 7:30, S246, complex variables for 3 consecutive Wednesdays, so we can cover the important stuff for your future. So complex bars, S246, Wednesdays, 3:22, 29, and I believe 4:05 or whatever the hell that Wednesday is. 7:30 to, I would say, 8:45 p.m., like hour 15. Complex variables, so but complex functions, we're talking about complex roots, the LNs, and stuff like that that we will need for, well, what's your major? Yeah, you'd be there. You said computer science, I didn't do it. Why would you sit in differential equation computer science? Just for intellectual curiosity, right? That's the best way to explain it. That's what my admiration for students comes from. I put a senior class, which is classical. Computer science, otherwise there's no need to use it. You have to take it. Computer science, you must take discrete, and you must take linear. I don't care if they say one or the other, you must take both. That's the bottom line. You want to be any good in programming or algorithms, proofs, relationships, you got to know them all. Do what?
No.
Well, you said twice the same thing, and it sounded like you spoke Japanese, so I didn't catch any of the words you said.
You got it there. Gotta catch them all.
Oh, there we go. All right, fine. That game is dead right by now, right?
Yeah. I really hope so. Well, I think, well, actually, no, Steve's still on it right now.
Oh, he's still playing.
Yeah, Steve's still playing. There's like 4 or 5 people playing at this school. That's it?
Used to be like 100,000.
Yeah.
Just at RV. Well, they made the game, they made the money quick in this pull out. And now let it coast.
My friend said that they were going to bet a game like that. And it was basically just going to be like almost like a laser gun kind of game where you kind of like, if someone comes up to you close that also plays the game, your phone says like 3, 2, 1, and then you like have to like draw and try to like shoot the kid. But like I was like, wow, that could lead to so many different issues. Yeah, you should have down, bro. Like
drive by.
No, you're just going into your pocket and just be like pulling out something real quick. That's just like
Oh, imagine if you are pulled over for speeding and you and cop are both playing the game. Oh. That would be,
he goes, wrong pocket.
unfortunate. Wrong pocket, yeah. You shoot the laser, he shoots the real gun, see who makes it together.
And the great part is it's all in his face.
Yeah, there are many good ideas, right? This is just a ton of mess in these problems.
I was reading this magazine, and it said I think it was one of the countries in South America. People had to start moving out of the mountains because they were drying up. There was like a glacier down there that dried up like in 2009, so they don't have any water. And there was this one invention that this guy made where you can pump. It's like a pump system, and it pulls moisture out of the air, and you can make like 12 gallons of like fresh drinking water daily.
So now they're not gonna have drinking water, and they're gonna have dry air too.
Yeah.
It's gonna have no moisture, and their skin is gonna be dry. And let's not get into. Oh, how long is this problem actually? There we go. Be happy to announce in my algebra class that in 2 hours I managed to finish 3 examples in class. Algebra is like 3 examples per 5 minutes. All right. So as I said, these recurrence relations can have 2 terms, 3 terms, multi-term, right? So here are problems 23 through 27. They all say to solve, and then you will get a 3-term recurrence. So all right, let's believe them. Since we don't have infinity of time, I would like to do either number 23 or 26 because they only have 26, yeah. So 23 or 26, they only have 2 terms to begin with. How about I do 26? Yeah, I'll do 26 because 23 is easier, so you can try that one at home. Guys, some of these homework assignments you should be really grinding. Especially now you see how long it takes. What was the formula? If professor can do it in X amount of time, student when learning is about 4 times as much. So if it takes me 15 minutes to do a problem, yeah.
His exams for circuits are I've never like gotten to like the key of like time. I've never done that.
You really got to know what you're doing. You don't really have time to stop and then think about it for 5 or 10 minutes. Like you just have to go and do it, otherwise you're gonna run out of time. At least for that one.
Damn.
Yeah, that was really time.
You didn't know what you were doing.
Well, the good thing is that the circuits really trained you for the second exam in differential equations, right? You're gonna stop on a 30-minute problem to think for like another 30 minutes, and then you have 9 problems to go. No, we're gonna do like 3 problems for this test, right? You don't know which one is worse, right? Or make the exam 10 hours long with like 5 breaks and right, and a steak dinner in between or something for energy. I don't know what to tell you.
You mind?
See? No hesitation. All right, so what are we going to do here? We're going to do the same business as we did before. I'm going to have, we are going to assume that the solution is something of the form like this. Now, since they don't give us any initial conditions or anything like that, I'm not going to mess with x minus a. There's no need, right? And if there is, problem 27 does have initial conditions, but they're all at 0, so nothing special. I think all of the problems they give us with initial conditions. No, -2, so you will go x plus 2 for problem 21. Yeah, expand around x plus 2. All right, cool. So this is 0 to infinity. Y prime is 1 to infinity n cn x to the n minus 1. I'm not going to shift it now. I'm going to see if I need to shift and then do it. So when I plug this one times a cube, it's going to be n minus. No, it's going to be a lot of dancing around on this one. Such is life. All right, here we go. I'm not going to shift anything. Just plug everything in and then see what I have to do. So this is it. You know what? I can distribute. Nah, I'll write 2 to infinity n minus 1 and cn x n minus 2 plus x to the 4th power summation from 0 to infinity. This is the vanilla state equal to 0. Oh, by the way, can you have this equal a force function? Yeah, and then what do you do? Move it to the left. I know, right? It doesn't have to be a 0 there. All right, so now we distribute both of these. The first one will just be 2 to infinity n minus 1 n cn x n minus 2 plus, and now I have x cubed, which I'm going to distribute immediately inside. And this becomes x to the n plus 1. The counter still goes at 2 to infinity. And when I bring this x inside, summation cn x to the n plus 4 equals to 0. This one starts at 0. So you have to be very careful where your counters start, so you are able, so you can peel off appropriate number of terms. Great. So now what do I have to do? I have to make this x to the n, and I will achieve that with the substitution k is n plus 1. And over here, k needs to be n plus 4. And then I will just rename it back into n's when I'm done with transformations. And this one is n minus 2. To bring that one back to n, I need k equals n minus 2. So now I have to use these shifting and substitutions in all three to bring back. And then we'll see later what we have to peel and where. So now this is n equals to 2. So I need to subtract 2 on both sides. I get k equals to 0. And then n minus 2. So what's n? N is k plus 2, so k plus 1. And then k plus 2. And then c k plus 2. And then x to the k. Awesome. First one done. Next one. This is n equals to 2 again. So that's just going to be k equals 0 right away. I have n minus 1. We know that goes into k plus 1. The other one goes to k plus 2. C k plus 2. And then, wait. It's k plus 1 now. Good. This is just k. This is 1. This is k. K plus 1. ck plus 1. X to the k. Holy nightmare. Plus, shifting again, this is n equals to 0. I need k there, so k is equal to 4. So 4 to infinity. We said no coughing. C. N is k minus 4. And then x to the k equal to 0. Yay. So now all of my series have x to the k. Well, I don't have to shift it back to n. I can just keep it in k's. It's okay. I had to change all of them anyway. All right. So all of them, all of the x values are now to the k. Now I need to shift the counters. I have to peel off 4 terms for the first one, because look, k to the 4th, right? K equals 4 is the first one where they all agree, right? And the pattern will start from there. So now I have to go and peel 4 terms from the first, 3 terms from the second, and nothing from the third. K equals 3 for the second one. Let's see. If n, so n is equal to k minus 1. So k minus 1 is equal to, yes, you're right, k equals 3. Wow. You're right. What do you mean? All right. We'll talk after class. So for k equals 0, I have 1 times 2 times c2 times x to the 0 is 1 plus. So this is k equals 0. Now I need k equals 1. That's going to be 2 times 3 times c3 times x plus k equals to 2, which is 3 times 4 times c4x squared plus k equals to 3, and that's where we stop. 4 times 5, 4 times 5 times c5 x cubed. So now what I did is I peeled off all of the terms from the first one up to x, up to k is 4. Plus, and the summation that stays is k starts at 4 to infinity, k plus 1, k plus 2, ck plus 2, x to the k. Plus, now I have to peel 1 term from here, which is only k equals to 3. So I peel that off. That's 3 times 4 times c4 x to the 4 plus, and the remaining series stays, but now it starts at 4. And we have just plus, the last one starts at 4. And we finally got to the point where we have all of these to match. So this is it now. This is all one expression. And we put all of the numbers together, right? All of the non-series parts together, and all of the series combined into one. So I have what? 2c2 plus 6c3x plus 12c4 x squared plus 20c5 x cubed, and there was one more. There it is, 12c4 plus 12c4 x to the 4. So these are the terms that are out of series, and then plus overall series for all of these because it starts at 4. And now I have k plus 1, k plus 2, ck plus 2, plus k plus 1, ck plus 1, plus ck minus 4 times x to the k equal to 0. There we go. And your recurrence equation is inside these brackets. So we will observe that equation, right? Set it equal to 0 and go do the pattern starting with k equals 4 calculation. So k plus 1, k plus 2, ck plus 2, plus k plus 1, ck plus 1, plus ck minus 4 equals to 0. And I'm going to, I boxed each one of them in light red, so there it is. That's the recurrence. Equation. And they said in the problem 22 to 26, find the 3-term recurrence relation for solutions of the form. Then find the first 3 non-zero terms in each of the 2 linearly independent solutions. So they want the first 3 terms. Are we doomed that I have to do 6 of these? Because they said in each. I'm just going to swipe that under the rug and do first 4, I think. So we have to start with k equals to 4. That's our first number, right? Because as you can see, all of the summations now start with 4. So what do I get? I get 5 times 6 C6 plus 4 times 5 C5 plus C0 equals 0. Now this is equal to 30 C6 plus 20 C5 plus C0 equal to 0. Now, if you observe, C0 is understood as the known, and C5 is also understood as the known. So it's a C6. You always solve for the highest one. So C6 is equal to negative 20 C5 minus C0 over 30. That's C6. All right, K5. When K is equal to 5, we get 6 times 7, C7 plus 5 times 6, C6 plus C1 equal to 0. 42 C7 plus 30 C6 is equal to, no, plus C1 equals to 0, from where C7 is equal to minus C1 minus 30C6, which we know from the expression above, divided by 42, which is minus C1. And now if you plug in C6, see 30 and 30 cancel, and then negatives cancel across the board. So all I have is plus 20C5 plus C0. You can deal with this algebra when you get home, okay? It's a 42. And K equals to 6. I'll drop a mic and walk away. So that's 6 times, so 7 times 8, C8, plus 6 times 7, thank you, C7, plus C2, yes, equal to 0. 7 times 8, I believe, was 56 last time I checked, plus 42, C7 plus C2. Isn't it beautiful that this is actually going to cancel? So C8 is equal to negative C2 negative 42 C7 over 56. And now that's negative C2. And now again, the same trick. We are plugging now this in for C7. So C7, the negative and negative will cancel, so it will be plus C1. But then you will inherit the negative here, and minus C0. The 42 and 42 cancel, but then you still have the 56 down there. So C8 can be rearranged into a nicer looking expression by writing it as negative C0 plus C1 minus C2 minus 20 C5 divided by 56. So we got some coefficients. So what is our solution now? Y is equal to, you have to copy all of those terms that we peeled off up there. These ones. So y is equal to, you copy those, and then plus, and now go pick up your next term that we computed. Oh wait, this is, copied it to the side. Much better. And then we have plus, and then I have the next term, which was K5, which is C0 minus C1 okay, I'm experiencing lag now because it has too much series. Plus 20 C5 over 42. And this was for K equals to 4, so x to the 4th. No, x to the 5. No, x to the 4th. Right? That was the first we computed. Oh, I took the wrong one. You can never win with these things. It's just too... So I'll need this for later. That's the next term. So x to the 4th. And what it was? Minus C0 minus 20C5. Minus C0 minus 20C5 over 30. Then plus... Then the next one was this one, which is minus C1 minus 30C, no, C0 minus C1 was a plus 20C5 divided by 42. And then finally, that's x to the 5. That was one before, right? Yes. And then our last term that I computed is this one, so negative C0 plus C1 minus C2 minus 20C5, kill me now, divided by 56 x to the 6 plus, and that's going to go forever. That's your solution. You can put together all x to the 4s and right? Better have enough initial conditions to compute this monstrosity. I only went over 1 minute. It took me 21 minutes to do this. I didn't make any major mistakes, right? On this one. Good. Might be eligible to take the exam as well. All right, bye stream. I hope the stream was going. Yep, still helped. Good.